reason reproductive cloning doesn't work very well is because you have to take the old nucleus and you have to make it think that it's a young nucleus. You have to make it think it's a nucleus that's in an egg. This is a difficult process, and these nuclei are old nuclei, so a nucleus in your, say, skin might have lived so far for a number of years, maybe 40-some years, and so you have to take that old nucleus and try to make it young again, and we're not sure how to do that. That's one of the most difficult things about reproductive cloning. It's a very low success rate, maybe 1 to 2%. If you try to clone yourself.
Is that why Dolly was such a big deal?
Well, Dolly was a big deal because she was cloned. She also died at the age of 7, which is about half as old as a regular sheep would live. And so there's some idea that the nucleus was too old, and that's why she died at a premature age, is because even though the nucleus was tricked into thinking it was young again, it really wasn't that young again, and so she died.
You see, Mary and Tommy, reproductive cloning of human beings is a bad idea. The few clones that survive could have severe health problems.
Gosh, Mr. Sanders, that sounds terrible.
But, Mr. Sanders, wouldn't you like to be cloned?
Now, Tommy, would you really want to see another balding, middle-aged science teacher who lives with his mother walking around? That's my little cloning joke.
Oh, good one, Mr. Sanders.
Do you still live with your mother, Mr. Sanders?
Now, Tommy, what I'm saying is that cloning for reproduction is fraught with peril.
You know, Mr. Sanders, you are losing your hair.
Now, children, let's focus on cloning and not me, okay?
Have you ever kissed a girl, Mr. Sanders?
Maybe we should watch another segment of the Eyes of Nye science program.
Yes, Mary. Perhaps we should.
Are you crying, Mr. Sanders?
No, Tommy, I've just got something in my eye.
So what's the controversy then about reproductive cloning?
Well, I think there's really two controversies. The first controversy is, where do you get the eggs? So people are worried that there will be some sort of black market for human eggs, that young girls who otherwise might not give their eggs away will be induced to do that for money. So the source, where's the source of eggs, is one problem. And then the second one, I think, is the embryos themselves. When you understand human development, you'll understand that you cannot make a baby from those embryos unless they're implanted into a uterus. So as long as the embryo is kept in culture and kept outside of the mother, it will not make another human being.
Is there a place to draw the line?
For the Society for Developmental Biology, as scientists, we've come up with the rule that we're for therapeutic cloning and not for reproductive cloning.
When it comes to the technology of cloning, the train has pretty much left the station. See, once we perform somatic cell nuclear transfer, we get an embryo, not a fetus, an embryo, cells that are dividing. Now, there's two choices as to how we use that embryo. We can go this way. It's what we call reproductive cloning. Make a new cow or a sheep, or theoretically, even a person. But we don't have to go that way. If we don't implant the embryo into a womb, just let it grow, we can instead go this way. And this is therapeutic cloning. And the cells grow and divide. It's what we call stem cells. Now, stem cells can become any type of cell. Now, here's the thing. The procedure for reproductive cloning and therapeutic cloning is exactly the same up to this point. Up to this point, this fork in the road. If we go this way, we would get new people. If we go this way, we would get new cells. Which way do you want to go? Bill, if cloning is so risky and dangerous, why bother?
Well, Bill, if we were to perform a somatic cell nuclear transfer and fuse it so that it started to grow, we'd get an embryo.
We don't get a person.
No, an embryo, a ball of cells that's growing and dividing.
So we couldn't be talking like this.
No, this is an old TV trick. At 5 days along, an embryo has about 200 cells, and they're undifferentiated.
Undifferentiated?
Yes, they haven't started to become all the different cells of your body, like your skin cells, your bone cells, and your brain cells. They're stem cells, and they have astonishing promise.
But if you had to choose between, say, me and a bunch of stem cells, which one would you pick?
Okay, well here's the fun stuff.
So these are colonies of stem cells.
Right, these are human embryonic stem cells. Each one of these colonies derived from one single cell.
One of these back here?
That's right. That has divided and divided and divided and divided, eventually forming now a few thousand cells in a free-floating cluster, so that we have millions and millions of cells, all exactly the same. And then the next step is to change them first into brain, and then into a subtype of brain that we'd like for repair. So this is the center of one of those large clusters that is now stuck down, and as we move away, you can see very small little cells that all look the same, but then as we move further away, now we start to see them differentiate into these long, mature cells with long processes.
So what do we do with these cells?
Spin them down so as to concentrate them and squirt them into a spinal cord injury in a rat. So here's an animal that received an injury with no transplant. So this animal has not been transplanted, and you can see that he's not standing and just sort of drags his hind limbs around without any coordinated locomotion front to back.
Can't move his back legs.
Very little. It's not a complete injury. This models human spinal cord injuries that are the most common type of them, those sustained by like a car accident or a diving accident, sporting. It's called a contusion injury. So that's what we're trying to treat. It's a pretty severe injury.
So you injected this rat with the human embryonic stem cells.
That's right, that we first tricked to become brain committed and then to a subtype of brain that we know to support repair. Let me just show you what that looks like. This is a nice shot here because we can see that the legs are moving in a coordinated fashion, side to side. So it's not only a matter of controlling one side of his body, he can actually control both. And the tail is up, so he's got full control of his back muscles. And one thing you can't see in this video is that these animals regained control of bladder and bowel function earlier than the non-transplanted animals. That's the #1 concern of people in wheelchairs. But if we take an animal with a similar injury, only 2 weeks after transplant, you can see he's supporting his weight and standing, and you can see he actually takes some steps. Yeah, he's doing well.
So what's happening inside the rats?
Well, what's happening is that the cells that we put in are integrating into the spinal cord, and the spinal cord itself is growing through the injury in the transplant site, up above the injury site. So it's anatomical evidence for repair.
So how long did this take?
This took about 10 weeks.
So this works?
It looks like it's working. I'd say this is strong preliminary evidence that human embryonic stem cells have a real beneficial future.
Would you say you're in favor of therapeutic cloning?
Absolutely. I think therapeutic cloning could be to brain trauma and disease treatment what the jet engine was to the airline industry.
Good evening.